Hello, it's Stat 135, Lecture 23. So last time we looked at, in section, preliminary to section 9.5, we have a box that is binomial. So it is two types of tickets, say 0, 1, 0 and 1, with probabilities P1 and P2, where P1 plus P2 is 1. We draw n times with replacement. We get observed counts x1 and x2, where x1 plus x2 is n, and our expected counts are np1 and np2 because each cell is binomial. So our null is that we have a binomial cell probabilities P1, P2 in the box, and the alternative is that we have some other binomial cell probabilities in the box. So it is that kind of alternative. And the chi-squared test statistic is summing over all of the cells. We have observed minus expected squared over expected. And in this case, we have two cells. So we have a sum of 2 here. And as I showed before, with some algebra manipulation, you can write this as a sum of 1 term, where instead of np1 you'll have np1q1, and that will then be approximately a z squared, which is a chi-squared with 1 degree of freedom, which is the dimension of the sample space 2 minus 1. We have 2 boxes, but you have one constraint. Today we're going to further introduce these ideas, looking at multinomial cell probabilities P1 to Pm, and then we're going to really start section 9.5 on the generalized likelihood ratio test for multinomial distributions. So the multinomial random variable, we have a sum of n independent m outcome cells with probabilities P1 to Pm. They add up to 1. We're asking what's the chance of getting x1 outcome 1 and x2 outcome 2 and so on, where the sum of the xi's is n, and the answer to that is from the multinomial formula. We have n choose x1, x2, and so on, times the probability of p1 x to the 1 and so on. So if we know these probabilities, then the multinomial distribution is completely specified. In other words, when we calculate this, we actually get a number. If it's not specified, you would get something in terms of a parameter theta. So we have n trials, so we get observed and expected counts here, and since each xi is binomial npi, which is approximately normal npi and piqi, this sum will be approximately a sum of m minus 1 standard normals. And so I've written that below here instead of to go from m dependent terms to m minus 1 independent standard normals. The cost of doing that introduces a qi in the denominator. It's a little arduous to show that algebraically, but hopefully believe that based on m is 2 case. So now let's take a look at this table that we looked at when we did chapter 8.1. So here we were modeling the number of arrivals in 10-second intervals of a Poisson lambda process. So we can imagine we have this box with P1 lambda, P2 lambda up to P16 lambda. So these are the probabilities of getting 0 to 2 arrivals, 3 arrivals, 4 arrivals, 5 arrivals, and so on in a 10-second interval. Now, there's a total of 1,207 10-second intervals. And these probabilities are Poisson lambda, and so we computed lambda using an ML estimator. So we got mu to be 8.4, and so we could calculate these PKs using the Poisson formula. So now we know the probability for each of these counts, and we can find our expected counts then, because these expected counts, for example, these expected counts are binomial. N is 1207, and then pi, whichever row you're in. So for example, for the second row here, the distribution is binomial. The distribution of x2, I guess, is binomial 1207.022. So to find the expected counts, it would be NP, where p is 0.022. And so the probability that you get these x1 to x16 counts, observed counts, is given by the multinomial distribution. And so so we can calculate the chi-square statistic, which will enable us to either reject the null or accept the null, where the null is that we have these probabilities, our null box has these probabilities given by Poisson lambda, where lambda is our estimate. So what we see here is we get a test statistic, which is going to be chi-squared. The degrees of freedom is not 16 minus 1, but 16 minus 1 minus 1. The 16 minus 1 is the dimension of the sample space. The extra minus 1 is because our probabilities aren't completely specified. They're actually, there's a parameter lambda that needs to be estimated here. So that is you always subtract the dimension of the null space. This was a theorem in section 9.5 that we saw last time, but we'll talk more about that in next class. So let's jump into 9.5 now. So we have here, we're in a categorical case. Our box is categorical, unlike in chapter 11 where we had normal data, which is continuous. Here we have categorical data. We have a parameter theta, which may have k dimensions, and we get observed counts. So our first step is to estimate our parameter, and our second step is to find the expected counts. So our null is that we have a multinomial distribution, and this is called the null box. And so assuming the null box is true, we know what the expected counts are. They'll just be npi theta hats. The alternative is that you have some other different multinomial distribution. And so flashing forward, main result minus 2 log lambda, which you get from a generalized likelihood ratio test, will show is essentially a Pearson chi-squared statistic. So that makes that connection, and then we saw before that it is also asymptotically chi-squared with m minus 1 minus k parameters, where m minus 1 is the number of cells minus 1, and k is the number of estimated parameters. So finally, an example Hardy-Weinberg equilibrium model. So here our null box consists of, we have this probability model here where there's a parameter theta notice that the sum of these probabilities is 1. We observe some counts here that are actually phenotype counts, but they relate directly to the genotype. So the cells correspond, M, N, and N correspond to genotypes, dominant, hybrid, and recessive. So step 1 is we do an ML calculation and get 0.4277. Step 2, and then we can calculate these probabilities just using the formula of the Hardy-Weinberg model. And then step 2 is we find expected counts. To do this, we have our null hypothesis, which says that our null box is multinomial 1029 with these probabilities. And then we get observed, expected, and then we can calculate our chi-squared. We get a chi-squared that has a p-value greater than our alpha value, 0.05, let's say. So we would be accepting the null. So that's how this works. We will go into the theory of 9.5 next time. Have a great day.